Hello, this is John, and today I will be giving a video lecture about differential equations in motion. First, we will look over what a differential equation is. By definition, a differential equation is a mathematical equation that relates some function with its derivatives with respect to a variable. dy over dx equals fx is an example of a differential equation. Here, the function y is related with its derivative with respect to the variable x. The solution of these differential equations is defined as the antiderivative of the function. So basically the antiderivative of either side, or just simply the function y. In equation form, this would look like when the derivative of large f of x is equal to small f of x. As we know from previous lessons, we need this plus c constant because when we take the derivative of large f of x plus c, regardless of what the constant is ignored and the derivative becomes small f of x. So let's try an example and obtain the general solution of dy over dx equals 2x. There are many different antiderivatives and general solutions, so we need to approach this by thinking that what function, when taking the derivative, would equal to x. From our previous lessons of knowledge, we know that y equals x squared when taking the derivative is 2x. Thus, the general solution can be stated as y equals x squared plus c. On a graph, these different general solutions would look like this. The graphs are not very accurate, but you can roughly see that the slope of the tangent line of the curves at any x value are the same, but their function values are not. So, in order to come up with one solution to the differential equation, we need an extra piece of information, which often and usually is a point defined through which the solution curve or the antiderivative curve, or y, passes. So the combination of these two is called an initial value problem. So in this equation defined above, x naught is the x-coordinate of the given point, and y naught is the y-coordinate of the given point. So now I will try to solve an initial value problem and get a specific solution for an antiderivative curve. Let's assume that dy over dx equals 3x and y of 2 equals 6. From our previous knowledge, we know that the general antiderivative form of 3x equals y equals 3 over 2 times x squared plus c. Proceeding on from there, it can be stated that 6 equals y of 2 equals 3 over 2 times 2 squared plus c. Doing some more arithmetic calculations, we can see that c equals 0 for this problem. So thus, the c value is 0, and the antiderivative of dy over dx equals 3x when y of 2 equals 6 would be y equals 3 over 2 x squared plus 0. Now I will introduce a new topic related to differential equations. Equations of motion. When an object is dropped near the surface of the Earth, the acceleration due to gravity is 9.8 meters per second squared. This means that for every 1 second that the object is in free fall, it gains 9.8 meters per second of velocity. This can also be written like this: dv over dt equals negative g. We need the minus in front of the g because we're defining the direction up as positive. If direction down is defined as positive, then we don't really need the negative sign. Now let's try an example question using this concept. How long would it take for a ball dropped near the surface of the Earth to travel 15 meters? We approach the problem by first stating that dv over dt equals 9.8. And then, when the antiderivative is taken, we can see that velocity v equals 9.8 t plus c. But as you can see, I've purposely neglected the c because at time 0, the velocity needs to be 0 because the ball is dropped. And when t is equal to 0, c also needs to be equal to 0 for v to equal 0. The next step would be to calculate distance traveled as a function of time. We do this by stating that dv over dt equals distance, and then from there we could calculate that distance equals 4.9 t squared, which is the antiderivative of 9.8 t. Since the distance that we're trying to calculate for is 15 meters, we set 15 as d and solve for t. After some arithmetic calculations, we can see that the answer eventually is 1.750 seconds. Let us try another example. Shiwan throws a baseball vertically up on top of Summit Hall, which is 3 meters high. Calculate the maximum height as well as time taken for the ball to reach the ground. So we approach this problem again by stating that dv over dt equals 9.8. We obtain the antiderivative for the function, which is v equals negative 9.8t plus c. In this case, c cannot be ignored, as like the previous problem, because we have an initial velocity. The initial velocity is given at 15 meters per second, and this is when time equals 0. So when we substitute t for 0 and v naught for 15, we can, after some arithmetic calculations, we can easily see that c equals 15. So we set up the velocity equation again, stating that v equals negative 9.8t plus 15. This can be written slightly differently, like this. V equals ds over dt equals negative 9.8t plus 15, where ds is change in distance. Thus, after obtaining another derivative, we can see that s equals negative 4.9 t squared plus 15t plus c. In order to obtain c, we can again use the circumstances provided when time equals 0. Since height equals 3 meters when time equals 0, we can see that when we substitute s for 3 and t for 0, we can see that c would equal 3. Thus, our distance equation would equal s equals negative 4.9 t squared plus 15t plus 3. We can use the distance function to obtain the maximum height by employing the concept of the derivative. When the derivative of the distance function is taken, it becomes the velocity function. And we know that when the derivative of the function is 0, the original function reaches a local minimum or maximum, and the slope of the tangent line becomes 0. Since the distance function is parabola concave down, when the velocity function or the derivative function equals 0, the distance function would be at a local maximum, and thus the maximum height of the ball. After the derivative is taken, we can see that the velocity function is negative 9.8t plus 15, and after doing some arithmetic calculations, t can be solved to be 1.53 seconds. We can plug 1.53 seconds into the distance function, and it gives us 14.480 meters, which is the maximum height of the ball. We can proceed on to solve the other part of the question, which is obtaining the time at which the ball reaches the ground. So we can solve this problem also by using the distance function again. Solving for t when the value of the distance function is equal to 0, which would mean that the ball is at the ground. So we have this equation, so we solve for t using the quadratic equation, or using the solve function, or using other type of methods with the graphing calculator. And whatever method we use, we would end up with the value of t being 3.250 seconds. I hope you enjoyed the video, and thank you for watching.